Okay, hello everyone. In this video, we are going to discuss about shifting property or fast shifting property or fast translational property of Laplace transform. In our last class, we have been discussed in detail about linear property and corresponding numericals, change of scale property and corresponding numericals. So in this class or video, we are going to discuss shifting property. Then we are going to discuss Laplace transform of derivative. Then Laplace transform of integrals. So first we are going to start this one. So according to this property or theorem, if Laplace transform of f of t will be equal to capital F of s, if we are going to write capital F of s, then Laplace transform of e to the power at into f of t will be equal to capital F s minus a. So here is the proof. Laplace transform of e to the power at into f of t in general we can write e to the power minus st. This will be act as the whole function. So this will be e to the power at into f of t dt. So here e to the power minus st into e to the power at can be written as e to the power minus of s minus a into t f of t dt. So that implies Laplace transform of e to the power at f of t will be equal to capital f of s minus a. Why? Here you can see Laplace transform of small f of t will be written as what? 0 to infinity e to the minus st into f of t, or that this will be nothing but capital F of s. So here e to the power s is there, f of t is there. If e to the s, then it will be written as capital F of s. So here you can see f of t is there, f of t also is there, but here e to the minus of s minus a is there. So instead of s, s minus a is there. So we can write capital F of s minus a. Now we are going to use this property and going to solve two numericals. So here you can see that the question is Laplace transform of t to the power 3 e to the power minus 3t. If we are going to use this property, then how we are going to solve it? Here you can see. According to this shifting property, Laplace transform of e to the power 80 in general, e to the power 80 into f of t equal to capital F of s minus a. So first here you can first we have to consider which one is the function. Function is your ft. If I will compare this one e to the 80 ft and this one, so ft is nothing but tq, and here e to the power 80. If I will compare this one, so here a is nothing but minus 3. So first we have to find out what is the Fourier Laplace transform of tq. So Laplace transform of tq will be equal to 3 factorial by s to the power 3 plus 1, because we already know that Laplace transform of t to the power n is nothing but n factorial by s to the power n plus 1. So here t to the power 3 means 3 factorial by s to the power 3 plus 1, that is your 6 by 6 s to the power 4. But however, here it is e to the power 80 ft, that means e to the power minus 3t tq is there. So Laplace transform of tq is your 6 by s to the power 4. That means this is your capital F of s. This term is nothing but in the form of capital F of s. But if e to the power minus 3t will be operated on ft and we are going to take the Laplace transform, then according to this shifting theorem, wherever the s will be there, there we have to write s minus a. So as here a is minus 3, so we have to write 6. Here instead of s we have to write s minus of a is minus 3, so s minus of minus 3 to the power 4 is there 4. So 6 by s minus minus plus, so plus 3 to the power 4 is your answer. Okay, this question also you can do traditionally. How you are going to solve it traditionally? That means here it is given that e to the power t to the power 3 e to the power minus 3t, we are going to take Laplace transform. That means this is nothing but your e to the power minus st into tq into e to the power minus 3t dt, 0 to infinity, right? So 0 to infinity, so this will be e to the power, then this will be e to the power minus of s plus 3 into t into tq dt. Then we are going to do the by parts. Three times we have to do the by parts. That means here you can see, uh, if I am going to put the islet inverse logarithmic arithmetic trigonometric exponential, so this will be the so-called the tq will be fast function. So first time if I am going to do the integration, tq integration of this one means e to the minus s plus 3t divided by minus of s plus 3. Okay, then 0 to infinity minus derivative of this one 3t square and integration of this one, that means 1 by minus of s plus 3 into e to the power minus of s plus 3 into t. So here you can see that this term will be 0, because if I will put infinite this term will be 0. If I will put 0 then this term will be 0. Then again by parts we have to consider for this one. Then again we have to consider by parts, because uh, second time by parts means we are going to get the t. Then third time by parts means we are going to get only t term will be cancelled out, and we are going to get s2 s plus 3 to the power s plus 3 to the power 4. You just do it, you can get the same answer. Okay, you can get the same answer, but in this way uh, the answer will be somewhat lingering. Okay, next we are going to consider another uh, numerical, that is your e to the power minus t into sine square t. We know that sine square t is nothing but 1 minus cos 2t by t. Okay, so Laplace transform of e to the power minus t into sine square t can be written as Laplace transform of e to the power minus t into sine square t can be written as this one 1 minus cos 2t by 2. So here this 2 is the constant, can be taken outside. 1 by 2 Laplace transform of e to the power minus t 1 minus cos 2t. If I will multiply with these two terms, then we can get 1 by 2 Laplace transform of e to the power minus t into 1 minus Laplace transform of e to the power minus t into cos 2t. Right, now we are going to use the shifting property. So here you can see 1 by 2 is there, 1 by 2. Now here you can see this term is in the form of Laplace transform of e to the power at into f of t. How? Here you can see, if I am going to compare this term and this term, here a is nothing but minus 1. Okay, f of t is nothing but 1. So Laplace transform of f of t means 1 is nothing but 1 by s, that we know. Laplace transform of 1 is nothing but 1 by s. Then using the shifting property, then what it will be? 1 by s, this is nothing but so called capital F of s. So using shifting property, this will be, that means e to the power at means minus t into 1, corresponding Laplace transform will be 1 by s minus a. That means 1 by, here a is nothing but minus 1, so s minus of minus 1, that is 1 by s plus a. Right, so that, or we can write, so this is f of s, no, so here this Laplace transform is nothing but f of s minus a, which will be this one. Same thing I have been done over here. By using shifting property, this will be this one, e to the minus t into 1 will be 1, the Laplace transform of 1 is nothing but 1 by s. Using the shifting property, that 1 by s will be s minus a. S minus of a is minus 1. So s minus minus 1. Likewise, here you can see cos 2t. Cos 2t, cos 2t Laplace transform. Laplace transform of cos 2t. Laplace transform of cos 2t, we know that s by a square plus a square. Cos 80. Cos 80 is nothing but s by s, a square plus a square. So Laplace transform of cos 2t will be s by a square plus 2 square. So this is nothing but capital F of s. So if we are going to apply for Laplace, your shifting property, then this shifting property, that means e to the 80 when it will operate over cos 2t, then this will be s my f of capital F of s minus a. That means s minus a by s minus a square plus 2 square. Same thing I have been done over here. Here you can see for cos 2t is nothing but s by a square plus 2 square. Using shifting property, wherever s, there we have to write s minus a. Here a is nothing but minus 1, so s minus of minus 1 by s minus of minus 1 whole square plus 2 square. So 1 by 2 is there already. So 1 by minus minus plus s plus 1 minus s plus 1 by this one is your s plus 1 whole square plus 2 square. For the simplification, we can get 2 by s plus 1 into s square plus 2s plus 5. This is your answer. Next, we are going to go for your Laplace transform of derivative. This one is your most important. Oftenly, this one also asking in your exam for 4 marks. So carefully you have to watch. And also the last expression, that means this one, Laplace transform of derivative, that means Laplace transform of nth derivative of the function. This one you have to remember, because this expression is required for solving numericals, whatever we are going to discuss in our next classes, right? So Laplace transform of derivative, that means here the first derivative of the function ft, that means f dash t. Laplace transform of f dash t will be s Laplace transform of ft minus f of 0. This is small f, okay? Or Laplace transform of f of t is nothing but capital Fs also we can write. So Laplace transform of first derivative of f of t will be equal to this one, can be written as s into capital F s minus f of 0. And second derivative will be a square into capital F of s minus s into f of 0 minus f dash 0. Laplace transform of third derivative of f of t will be s cube capital F of s minus a square f of 0 minus s f dash 0 minus f double dash 0. So here you can see third derivative means s cube, then s power gradually decreases, and last term is nothing but here third order derivative, here second order derivative 0. Okay, similarly in general we can write Laplace transform of nth derivative of a function will be, here you can see third derivative means s cube, nth derivative means s to the power n capital F of s minus, here s power gradually decreases, so this will be s to the power n minus 1 f of 0 minus, and 1 derivative increases gradually. So f of 0 minus s to the power n minus 2 f dash 0 minus s to the power n minus 3 f double dash 0, and so on. And last one, here you can see third derivative, last one is your second derivative of f of 0. So nth derivative means this will be n minus 1th derivative 0, f of nth derivative of f 0. Okay, so these all we are going to be proof. Okay, so here proof starts. You need to remember this one. Okay, most important, this one you have to remember. Now we are going to go for the proof of this one. Laplace transform of first derivative of a function, that is your, in general we can write 0 to infinity e to the minus st, this one f dash t dt. So as here f dash t is your unknown function, so e to the st will be considered as the first function, and then we are going to use the islet. So this is the first function, e to the minus st, 0 to infinity f dash t dt minus 0 to infinity derivative will of this one, integration of this one dt is equal to e to the minus st, then integration of this one, derivative of integration, that means same function ft. Okay, only derivative will be removed, 0 to infinity is the limit, minus here derivative of e to the minus st will be nothing but minus s into e to the minus st into integration of f dash t will be f of t dt. Here we can put the limit. If I will put infinite over here, e to the minus infinite will be 0, then the whole term will be 0 minus 0. If I will put 0 over here, this e to the 0 is 1 into f of 0. plus here minus minus plus plus s 0 to infinity e to the minus st f of t dt, right? Now that implies what we found, Laplace transform of f dash t. That implies Laplace transform of f dash t, this one minus this one. So this one is written as s into, this is nothing but capital F of s e to the minus st f of t, Laplace transform of f of t written as capital F of s minus this one f of 0. Okay, the first one we have been proved, this one. Then now we are going to go for the second one. The second derivative and its corresponding Laplace transform. We can write like this. Then as this is unknown function, so we are going to consider this is the first function e to the minus st, and derivative here second derivative. If I am going to consider integration, then one derivative will be removed, f dash t dt, f dash t will be there, will be come up, and we are going to put the limit 0 to infinity minus derivative of this one will be how much, minus s into e to the minus st, and integration of this one is nothing but f dash t dt. So here if I am going to put the limit, here infinite means 0, and if I put 0, then e to the 0 is 1 and f dash 0, f dash 0. So e to the 0 is your 1 into f dash 0, f dash 0 plus, here minus minus plus plus 0 to infinity e to the minus st into f dash t dt. So this integration already we evaluated over here, this one, this integration is nothing but this one. So I will be simply put this one over here. Okay. So hence what we are going to get is equal to minus of f dash 0 plus s into this much. Okay, so minus of f dash 0 plus s into f of s minus f of small f of 0. So this s will be multiplied with this one, so s square capital F of s minus, here you can see this s multiplied with this one, minus of s f of 0 minus of s f of 0 minus f dash 0. So finally we found Laplace transform of double derivative of a function ft equal to a square capital F of s minus s f of 0 minus f dash 0. Similarly, if you are going to go for the Laplace transform of f triple dash t in the similar manner, then you can found, that means similar manner means here we for this one we done the 2 times by parts. For this case you have to do 3 times by parts. So you can get s cube capital F of s minus a square f of 0 minus s f dash 0 minus f double dash 0. Hence, in general, we can write nth derivative and its corresponding Laplace transform will be here sq third derivative. So Sn capital F of s minus, here you can see s to the power, s power is gradually decreases. So s to the power n minus 1 f of 0 minus s to the n minus 2 f dash 0 minus s to the n minus 3 f double dash 0 and so on minus f of n minus 1 0, n minus 1th derivative of f 0. Okay, so hence right now we are going to go for the Laplace transform of integrals. Suppose we have an integral 0 to t f of t dt, then Laplace transform of this integral will be 1 by s f of s. So here f of s, capital F of s is nothing but Laplace transform of f of t. So to prove this one, let us consider phi t is your this integral 0 to t f of t dt. So if it is so, then phi 0 will be always 0 and f of t equal to phi dash t. See, phi t, if integration of ft, then its derivative will be, the integration will be removed and we are going to get f of t. So f of t will be f dash t. So here you can see that f of 0 always 0. That means whatever we are going to take the function and its integration, and if we are going to consider instead of t0, then it will be 0. I am going to show you some examples. You can see. Suppose phi t uh, phi t we consider 0 to t f of t dt, no. So here f of t consider t to the t 3 t square t plus 1. So integration of this one will be 3 by 3 t cube plus t square by 2 plus t 0 to t. Here 0 to t the integration is there, limit is there. If I will put, see, put, then what we are going to get, we can get also this one, t cube plus 3 3 got cancelled, t square by 2 plus t. Okay, and 0 if I'll put, entire will be 0, then this will be nothing but your phi t. So instead of t, if I will put 0, then entire term will be 0. Now if we are going to consider f of t equal to e to the t, suppose we are going to consider e to the t 0 to t, means e to the t integration 0 to t dt is nothing but e to the t, we have to put 0 to t limit, then it will be e to the t minus e to the 0 means 1. Then this is nothing but what, phi t. So if I am going to consider instead phi 0, then e to the 0 is 1 minus 1 will be equal to 0. Likewise, you can check that if I am going to consider f of t is e to the t plus e to the minus t plus 1, then also we are going to get the 0. And if you are going to consider trigonometric functions, suppose sin t plus cos t, also if I am going to consider the integration of this one 0 to t dt, then we are going to get phi t is this one. And if I am going to put phi of 0, also we are going to find out 0. Likewise, if we are going to consider f of t will be equal to ln t log t plus 1. So log t is nothing but, integration of log t is nothing but ln t into t minus t, and here 0 to t, and here 0 to t. So if I will put the limit, upper limit, then the answer will be how much, phi t will be equal to ln t into t minus t plus t square by 2 plus t. Then if I will put 0, the entire term should be 0. Then phi 0 will be equal to how much, will be 0, because here t is there, t, so 0. So here we found that if phi t will be this much, phi 0 will be 0, and f of t equal to nothing but phi dash t. Now we are going to consider Laplace transform of derivative. We can found Laplace transform of f dash t, sorry, phi dash t. So here we found Laplace transform of f dash t is capital F s minus f of 0, small f of 0. Similarly, instead of f, here phi dash t, so Laplace transform will be s capital phi s minus small phi 0, right? Now, so this is nothing but Laplace transform of small phi t. So here s into Laplace, this one, Laplace transform of small phi t minus phi 0. Phi 0 always 0, right? So we found Laplace transform of ft, because f dash t is nothing but ft. So ft, Laplace transform of ft equal to s into Laplace transform of phi t. Laplace transform of ft will be equal to s into Laplace transform of phi t, because this is 0. So Laplace transform of phi t will be, this s will be divide this side 1 by s, Laplace transform of f of t, small f of t. So here Laplace transform of phi t will be 1 by s, Laplace transform of f of t is nothing but f of s. So that implies, first initially we consider phi t is nothing but this integral. So instead of phi, we can put Laplace transform of 0 to t f of t dt will be equal to 1 by s f of s, hence proved. So I suggest that watch carefully this video and write down the note. Oftenly in your exam, to prove these properties, asking for 2 to 3 marks. So write down, and we are going to do some numericals on these properties in our coming classes. But next class we are going to discuss another property, that is your derivative of Laplace transform and integration of Laplace transform. Okay, so thank you so much for watching this video. Thank you.